Let's take a couple of two-dimensional vectors. I'm going to call them u and v. And let's let those vectors be 1, 2, and -2, 3. Let's plot those. I'll do u in pink. So I have 1, 2. 1, 2 is about there. And I'll do v in blue. -2, 3 is here. And if I add those two vectors together, or if I create a linear combination of those two vectors, I'm going to have some scalar times u plus some other scalar times v. And what that really does is, let's go with 2u minus 1v. That's a linear combination of u and v. What that does is it doubles the length of u. So that's going to be something like this. And it flips v in the opposite direction. So I'm going to have v coming down here. And because I'm adding these two things together, my resulting vector is what I would get by closing off or completing the parallelogram. So that is going to be this vector here. Okay, so that's 2 times vector u minus 1 times vector v. But what if I said negative u plus v? Well, that's going to look like this. And my resulting parallelogram looks something like this. So I get this vector here. And then what if I said, actually, I could do this forever, right? There are actually, in this environment, in this context, there is actually an infinite number of ways that you can combine the vectors u and v. I can take 1, 2, 3, 4, 5, 6, 6.1, 6.2, pi. I can take all of those numbers as my scalar for u, and I can take this as many numbers, the same numbers in the same or a different order as my scalars for v, and I can add them together as, 1u plus 2v and 2u plus 1v and 2u plus 2v and so on and so forth. There are an infinite number of ways that I can combine these. Now, with an infinite number of possibilities and an infinite number of combinations, it's not possible to do that literally, but I can say that if I find let's just call it the terminal point of this vector, and then a terminal point of that vector, and I find the terminal point of another vector and another one, based on scaling u and v, I am essentially going to get the entire plane of R2. These points are shorthand, right? These are the endpoints of vectors. But my point is that if I did this long enough, I would have vectors that reached out to every point on the R2 plane. So I have the entire R2 plane. What we say about the collection of all possible linear combinations of u and v, let's call this a set. Let's call this the set S, the set of these two vectors u and v. And I'm going to say about this set that if I can find all possible linear combinations of the vectors in the set S, then I have what is called the span of S, the span of the set. And we write that as span S. It almost looks like function notation. Now, it's worth noting that this span of S is itself a collection. It's a collection of all the linear combinations of those two vectors. And so I think what I'll do here is call the span of S, which is a set, I'm going to call that V. And when I do that, we say that S is the spanning set of V. We also say that V is spanned by S. These are really all just sort of similar ways to say the same thing. Now there is an exception here, but I'm going to stick with this just for a little while longer. I'm going to say I've got a third vector. Let's call it W. And maybe I'll even give it some coordinates. How about -3, -4? That vector is going to be, about here. The thing is, I can talk about the linear combination of u, v, and w, or all the possible linear combinations, but u and v are already enough to encompass the entire plane. So if I add v to that, or w to that mix, I'm not gaining anything, right? The span of the set u, v, and w is still all of R2. So I can say that the span of S is equal to R2. This is where the exception comes in. But again, I'll come back to that in a minute. So with the exception of my exception, the span of all two-dimensional vectors is the two-dimensional plane. Those two vectors are in that plane, and so the span of those two vectors makes up the plane. All right, let's talk about that exception. If I have two vectors, the span of those two vectors is the entire plane that those two vectors are sitting in. If I have two or more vectors, if I have 3 or 4 or 5 vectors, I'm not gaining anything because I already have the entire plane. So having only 2 vectors is the same as having 3 or 4 or 5. The span of the set containing those 2 or 3 or 4 vectors is all of R2. What if there's only one vector? If there's only one vector, then I can only, my set is only contains one vector. And all the possible linear combinations of the vectors in this set are just some scalar times the vector. And what that means is that all I have here is a series of extensions, scaled versions of u. And so my endpoints all line up on a single line. So if I only have one vector, the span is not all of R2, it's a line. Equally, if I have two vectors u and w, but w is just u scaled, well, that's going to give me the same thing, right? Because if I have a1u plus a different scalar times w, well, w is already just a scaled version of u. So I get a1 u1 plus some other number, I'll just call it k for now, times u again. And that gives me a1 plus k times u. That's just a scaled version of u. So two vectors doesn't always span the entire plane. Sometimes it only spans a line. There's no exception. It's one of those two things. Either you have two vectors that are not scalar multiples of each other, and the two vectors then span the entire plane, or one of the vectors is a multiple of the other, and the span is just a line. So that's what happens in R2. What happens in R3 is a little bit more interesting, although it's not really very different. It just feels a little bit different. The span of one vector in R2 forms a line. And I don't know if you noticed, but that line is always going to go through the origin. Well, the same is true in R3. A vector in R3, you could call it U, I suppose, if you scale it and stretch it and flip it around, and every time you do that, you drop a point, those points are all going to end up on a line. So one vector, even in R3, has a span that's just a line. Similarly, just as in R2, if we have two vectors, but they line up with each other, then the linear combination of those two vectors is also just going to be a line. So if you have one vector or two vectors, one of which is a multiple of the other, vectors that are scalar multiples of one another, the span of those two vectors or the span of that one vector is just a line. If the two vectors are not multiples of each other, though, then their span is going to be more than just a line. I'm actually going to try to draw a little shadow here so you can see what that vector is supposed to be pointing out over the xy plane. Here what I've drawn is just the sum of u and v. And that works as a linear combination because that's just one u plus one v. That's a linear combination of u and v. So my white vector here, the sum of u and v, is in the span of u and v because it's a linear combination of the two. There are lots more vectors in the span of u and v. In fact, there's an infinite number of them. But the thing we have to keep in mind in R3 is that even though we're allowed to move around in 3 dimensions, the vectors u and v still have a set direction. I can scale v, I can make triple its length, make it really long, and maybe make u go in the opposite direction. When I add those two together, let's just do that very quickly. I'm going to triple v, and I'm going to make u go down here. When I add those two together, I get a vector that comes out here. So there are lots more vectors in the span of u and v. But because u and v have fixed orientations, sure, I can stretch my arms out. I can stretch my vectors out and reach points farther and farther away, and I can reverse the direction by negating one of the vectors and reach in the opposite direction. But because of the fixed positions, the fixed orientations of u and v, I'm still going to end up with a plane. Even though I'm in R3, the span of u and v is just a plane, not all of R3. So far we have this. The span of one vector in R2 or R3 is a line. The span of two vectors that are collinear, that lie on top of each other, both in R2 and in R3, is a line. The span of two non-collinear vectors in R2 and in R3 is a plane. In R2, it's the xy plane. In R3, it's a plane, well, it could be at an angle. It's kind of hard to describe without drawing a picture, and I just don't have those skills. But the punchline so far is that the span of one vector is a line, the span of two collinear vectors is a line, and the span of two non-collinear vectors is a plane. And that's true of both R2 and R3. Where it gets a little bit different, though, is that in R2, if we add a third vector, we don't gain anything. We already have the entire plane from two vectors. But in R3, something else does happen. In R2, when I add a third vector, that vector has to be on the same plane as my first two vectors. There is only one plane. It's the xy plane. In R3, my third vector can point in a third direction. And so that gives me a little bit more room for moving around. Remember that I said that the span of two vectors, two non-collinear vectors in R3 was a plane? But the reason for that was that their orientation was fixed. You can add them together and scale them in as many different ways as you want, but you can't change their direction. Once you add a third direction, you add a third dimension. And so if you imagine taking the first two vectors and finding the span of those, you'll end up with a plane. Take that third vector, though, because it's not on the same plane, what it's going to do is move the span of the other two in its direction, forward and backward in its direction. So you end up then with the entirety of R3. But you need, in order to do that, 3 vectors going in 3 different directions. Theoretically, we could talk about the span of 4 vectors in 4-dimensional space being what we need to span all of R4. We've talked a lot now about what a span is, what it means to be the span of a set of vectors. But how do you tell if a given vector is in that spanned space? Here's one way we might write a question like that. Here's a vector, 0, -1, -1. Is that vector, let's call it A, in the span of these other 2 vectors? We'll call them U and V. Well, if it is, then A has to be a linear combination of U and V. And so that means that there has to be some constant times U plus another constant times V. It's going to equal my vector A. Well, that's my linear combination, but remember what this means. This is just vector U, 1, 2, 0, and here's vector V, 0, 1, 1. I want a combination of those that when I add them together, scale both of those, and when I add them together, I get the vector 0, -1, -1. So my job now is to find a constant to put here and a constant to put here to make this statement true. Can those constants be found? Well, why don't we call them x1 and x2? And then what we have is a system of equations. x1 plus 0x2 equals 0, 2x1 plus 1x2 equals -1, and 0x1 plus x2 equals -1. Well, I only did that because I wanted to remind you that that's what we're doing here, that's where all this stuff is coming to. You know, we started the quarter, we started the term with basic ideas of matrices and how to solve augmented matrices to find out what their solutions are. That's really still all we're doing here. If you forget that that's the goal, then it's easy to get lost in all of this terminology and notation. But ultimately, what I'm looking for here is, because I'm looking for something in the span of the 2 vectors u and v, I'm looking for a linear combination. And in fact, I'm looking for the particular linear combination that produces this vector here. So what I want then is the solution to this system of equations. And we know how to solve a system of equations using a matrix. Let's rewrite it as 1, 0, 0, 2, 1, -1, and 0, 1, -1. If I do some elementary row operations on this matrix, I'll end up with this matrix. And at first, it might look like there's no solution here because these 2 rows are the same. But in fact, I only have 2 variables. So what this first row tells me is that x1 plus 0x2 is equal to 0. x1 is equal to 1. x1 is equal to 0. What the second and third rows tell me is that no x1 and 1x2 equals -1. So x2 equals -1. So since I have found a solution to this matrix came from this system, and this system came from this linear combination. This linear combination has constants C1 and C2. I renamed them x1 and x2 for convenience and familiarity. Those exist. They are 0 and -1. Therefore, the vector that I was working with here, this vector A, is in the span of these 2 vectors because it is a linear combination of those 2 vectors. Now, you may have spotted, I think I want to move this piece. Let's put this solution up here. You may have spotted that vector v is actually just the opposite of vector A. That means I can write A as being equal to 0 copies of vector u minus 1 copy of vector v, and that is also a linear combination. In this particular case, I didn't need to go to all of this trouble. I did it anyway because this will not always be quite so straightforward. It may not always be this obvious. In fact, usually it will not be this obvious. So it's good to know what the process is and what we're actually looking for. But if you can make an observation like this, then there's absolutely no harm in that either. The thing that's key here is recognizing that A is a linear combination of u and v. However you come to that conclusion is irrelevant. One last thing, this relatively minor seeming point is kind of important, so I do want to talk about it. Let's take a set of vectors 1, 0, 0, and 0, 1, 0. I could even throw in a third one, 0, 0, 1. Those happen to be my I, J, K vectors, my basis or standard unit vectors. Together, these three vectors form a subset of all the vectors in R3, but they do not form a subspace. In order to be a subspace, the 0 vector has to be included, and it is not present here. So this is not a subspace. It's a subset, but not a subspace. The cool thing, though, is that if I take these three vectors and I find their span, well, their span is made up of a whole bunch of vectors, all the possible linear combinations of these three vectors. And remember that since these three vectors are non-collinear, this one goes in the x direction only, this one goes in the y direction only, and this one goes in the k direction only. They're non-collinear. None of them is a scalar multiple of the other. So together, these are going to span all of R3. And remember that the span of a space, the span of R3, in this case, is a linear combination of these vectors. And linear combinations of vectors, let's call this one, I'll just call them I, J, and K. I've got A1I plus A2J plus A3K. One of the many, many, many linear combinations of I, J, and K is 0I plus 0J plus 0K. And that's the 0 vector. So although the three vectors themselves are not a subset, the span of a set of vectors is a subset, a subspace. Let me write that again just a little bit more accurately. The span of a subset of Rn is a subspace of Rn. What's sometimes hard to remember about spans is that the span of a collection of vectors is another collection of vectors, but that collection, the span, is much bigger than the original collection. Because I can scale these and add them together in lots of different ways, the span of this set is much bigger than the set itself.